Hello, I'm James Ingram for AutoControls.org. Welcome to video number 813, which shows an S-gauge DCC automatic passing sighting in operation. Note there's a previous video number 811, which shows a large-scale automatic passing sighting in operation. Also, there's a video number 812, which shows a large-scale 3-track automatic yard in operation. This video is almost the same as video number 811 with the large scale, except for two differences. One thing, we're using different accessory decoders here because you need a different accessory decoder for the S-gauge turnouts than you do to throw the large scale turnouts. The second difference, and that's necessary, the second difference is by choice. In this video, we're just using one reed switch back in the rear to do all our signaling to the mini panel, whereas video number 811 with the large scale uses 2 reed switches. You can really do it either way, and each video shows how it works with that number of reed switches. In video number, also one more difference in the two videos. In video number 811 with the large scale, we ran the trains in 2 directions. In this video, we're running in 1 direction all the time. If you want to see 2-direction operation, which would be possible with this system, please refer to video number 811. Finally, there are links down below this down below this video in the text description. There should be links to the PDF files for the drawings for the wiring diagrams, and also the list of commands used to operate this little system. Thanks for watching, and hope you find something interesting. Here's the control board for this system. This actually was used earlier in video number 806, this control board, but we're using it again for this video. Our most important component, I guess, is right here. This is the NCE mini panel. It's a little consumer level programmable controller, I guess you could call it, for DCC. Out here is another one of the same items in a package, and this thing's an off-the-shelf component. You just go in and buy it off a rack in the hobby shop. I think it has about a $49 list price. It's nothing exotic. It's an off-the-shelf item, mass production. And you do have to use it with an NCE system. It won't work with a Digitrax command control system or a Lens command control system. It does have to be an NCE command control system you use it with. But now here's the good point. You can use it to operate any one of 20 or 30 different brands of decoders that follow the NMRA DCC standard. That's a good point. As long as the engines have a decoder that follows the DCC standard, this controller will operate it. Getting back to our control board, this one has the accessory decoders. Here's a snap-it for the one turnout, and here's a snap-it for the other turnout, and they've got extra capacitance added to get additional current flow necessary to throw these S-gauge switches. We'll talk more about that later. The wiring for these is actually a little simpler if these are out on the layout, but this was made to interface with a layout, and that's why they're back on the control board, so we could bring this thing up and mount it to a layout. But at any rate, here's our 2 accessory decoders that throw the remote control turnouts. Over here is our NCE power cab, which is essentially our command station. It's basically a entry-level command station. The cab and the command station are all built together as one unit, which is what I've got in my hand here. And part of that is what they call this thing here. They call it the power control panel, which brings the power into the system. And then looking out here, we have our converging turnout where the 2 sidings come together. Going down our sidings, we can see at the end down there is our diverging turnout, and the reed switch is down there. And these blocks of wood here, the purpose of those two blocks of wood, they mark where the engines stop on the sidings, just to keep track of how far they're rolling under momentum. Moving down to the other end where the diverging switch is, where the trains come into the siding, we have our reed switch just upstream of the diverging turnout. You can see the reed switch here. If I pull it out, I think this is a Railroad Concepts reed switch, or it could have been obtained from DCC bit switch. The reed switch is actually, the reed switch itself is typically a little glass tube, and what whoever provided this thing did is enclosed in a protective rubber housing, but there's a little glass tube in there, a standard reed switch. You can get these from many places. You can get them directly off of eBay or from hardware supply stores. One important thing to mention, and we'll talk more about this later, but with the reed switch being located down where it is, just upstream, you could say, of the diverging turnout, we can use one reed switch to control both trains coming into these sidings. But basically what we do when the engines go over that reed switch, we send them a set speed 0 command. In other words, we tell the engine to go speed 0, and then we use the engine's momentum to have it pull into the siding and stop at the appropriate spots, which is by these blocks. So we're depending on the engine's momentum to get it into the siding. And the only key thing is we need to make sure our engine doesn't lose electrical contact coming through the turnout, because once it goes over the reed switch, it's got a set speed 0 command. So if it loses contact and then it regains contact, it's sitting there with a speed 0 command, and it won't go anywhere, and it'll mess the operation of the system up. Just one quick comment about this siding, the way it's built. This is one of the S-Helper Service track plan sheets, and this is all for the sharpest radius, 19-inch, they call it 19-inch radius track. But if you use a 19-inch radius track to build this siding like we've got it here, they show a 2 11/16 inch long makeup piece being required, which means you're supposed to cut a piece of track. And me not being particularly skilled at cutting track, I was looking for an option to not have to try to butcher up one of my pieces of S-Helper Service track. And what I found is that right here, this piece here, if I substituted a piece of the 24-inch curve, which is slightly longer, for the 19-inch curve, I can make up that section, and it seems to work okay. Here's the 19-inch curve that you would normally use, since all this rest of this layout's 19-inch radius curves, and there's that 2 11/16 gap you're going to have. But instead of using the 19-inch piece, you put in a 24-inch radius piece, it just seems to work okay to fill up this gap, and you don't have to cut any track. We were looking at the reed switch a minute ago. To activate the reed switch, that is to say to close it, which is what sends the signal to the mini panel, you've got to have a magnet somewhere near the front of the train. In the case of this steam engine, there's a magnet you can maybe see located right here on the front truck. It's one of those little round magnets, and in this case the truck is made out of metal, so the magnet just sticks right to the truck without any glue or anything. Other places you can put them on these engines, or sometimes on the drawbar. If you have a metal drawbar, you can stick the magnets here, or sometimes we've stuck them on the tender if the tender has a metal floor. If you're using an analog system where you're running DC trains and you're using blocks in the track to stop the trains, your magnet needs to be, it's usually a good idea to have it on the engine. In this case, for this video, we're running DCC, not analog. We're not using blocks. There's no blocks in this system. We're just using that reed switch back there to signal that we want to stop the train. Your magnet can be almost anywhere as long as it's somewhere near the front of the train. For the passenger train, what we've done, we glued one of those brown magnets, hot glued it on the bottom of this passenger car. This is the one that follows behind the engine. And this is hot glued. With this hot glue, you can peel these off here usually without damaging anything. The hot glue is strong enough to hold the magnet on, but it's not strong enough that it'll damage the plastic if you pry the magnet off. Another place we've sometimes put the magnet is on these American Flyer freight cars. These American Flyer freight cars, the newer ones, they have a nice free-rolling wheel, but they still got a metal truck, and sometimes you can put the magnet right on the metal truck. It'll stick there and do its job as a magnet, again with no glue. The trickiest part with these is they're a devil to get off because that magnet holds so sturdy. You've got to get in there with a screwdriver and work trying to pry these magnets off. So once they're on there, like this one, it's almost easier just to leave it on. These round magnets we've been using seem to come in two common sizes, and again, I think I've got some of these from DCC Bit Switch and got some from Railroad Concepts. I believe you can also find them on eBay and other places. They're very powerful. If I put this magnet down next to this piece of metal track, you can see it just sucks it right up, and it holds it very securely. There's a little test routine in the mini panel written such that if we hold a magnet over the reed switch, it should throw these two turnouts 4 seconds apart between each one, and we actuate that with push button 2. Fred Cupp, the guy who does all the hard work around here to put this stuff together for me, installed 10 push buttons on here, so we have push buttons 1 through 9 to activate inputs 1 through 9, and then the last button is a reset. But I'm going to push button 2 here, which should start that test routine, and I'm going to walk down here and hold the magnet over the reed switch, and you can see what's happening. Both those turnouts are throwing. Each turnout's throwing 4 seconds apart, and they're staggered, so you get 2 seconds between turnout throws. And we can't go any sooner than 4 seconds because we got to charge those capacitors back up to get enough current. But this basically verifies that your reed switch is working and you're communicating with the mini panel without having any trains. And you can actually run this test without even having any track, which will demonstrate that later. And if I pull this magnet away, that'll finish going through the cycle and stop throwing the turnouts. If I bring the magnet back down, you can see it starts up that test sequence again. And again, pulling the magnet away stops the sequence. That's just a test sequence to verify your reed switch is communicating with the mini panel. We'll start the demonstration here. The logic of this system is it'll throw the turnouts to curved. They're already curved at the moment, but it'll throw them to curved, start that steam engine on the inside loop, run it around the loop, and when it gets to the reed switch back in the rear just before the diverging turnout, it'll send a set speed 0 command to the steam engine, which will tell it to stop. The steam engine will coast in to the siding and park again just about where it is now. Then it'll delay about 16 seconds between trains. Then the mini panel will send a signal to throw the turnouts to straight. It'll start that diesel on the outside loop up and run it around the loop, and again it'll wait till it reaches that reed switch back there before the diverging turnout. At that point in time, it'll send a set speed 0 command to the diesel, which will tell the diesel to stop, and the diesel will come in and stop again about where it is now. At that point, the cycle will repeat itself. It'll start the steam engine up. It'll actually throw the turnouts to curved, then start the steam engine up, and so on. I'm going to push the run button over here on the control panel, which is just out of the camera's view. Now, as that steam engine approaches that turnout down there, the magnet on the bottom of that engine will go over that reed switch, send a signal to the mini panel, which will set the speed to 0 for the steam engine. In other words, tell it to stop. Now that happened, and it's rolling into the siding under the momentum control, stopping about where that piece of wood is. Now we'll delay approximately 12 seconds. The turnouts went to straight. Now the diesel is starting up. Now the diesel's out on the main line, and again, when the magnet on that passenger car, there's a magnet on the first passenger car. When that goes over the reed switch, the mini panel sent a set speed 0 command to the diesel, and the diesel will roll in under momentum slowdown and stop. There it stopped. Now we've completed the first cycle. We'll wait a few seconds. There the turnouts just went to curved. Now we're starting up on the second lap of the steam engine. Now we're doing the second lap with the steam engine. The magnet on the steam engine is stuck up under the front truck underneath the front of the engine. Now it's about ready to go over to the reed switch. It's gotten its set speed 0 command, and it's ramping down under momentum control. Now we'll wait a few seconds and throw the turnouts to curve. Turnout just went to curve. The mini panel is starting the diesel up. Now the diesel's out on the main line. The magnet for the passenger train is mounted under the front of the first passenger car. Now it's about ready to go over to the reed switch. The diesel got a set speed 0 command, and it's ramping down under momentum control. Now our diesel stopped. We'll let this go for a third cycle. We've completed 2 cycles. There's the turnouts went to curve. Now the steam engine's starting up for the third time. Okay, we're approaching the reed switch with the steam engine. Magnet went over the reed switch. Set the speed to 0. It's slowing down. Rolled in and came to stop. And the delay is adjustable between trains. There's a delay statement in the mini panel. I think I have it adjusted for about 16 seconds, but you can change that delay to make it wait longer between trains if you like. Again, magnet on the passenger car approaching the reed switch. Right about now it got a set speed 0 command, and it's ramping down to a stop. You can see that diesel, it shifts a few inches forward or a few inches backward each time when it stops, but it stops generally in the same area. Now I think we're on our 4th cycle here. We'll let this run another lap. Okay, trailing truck went over the reed switch. Steam engine got its set speed 0 command. It's slowing down. In a minute, the turnouts will go straight for the diesel. There they go. Now the diesel will start up. Now once that diesel goes over the reed switch over there and it gets its set speed 0 command, I'm going to push the reset button on the mini panel, which will stop it. Now I just sent a reset command to the mini panel, which stops the sequence it was running in the mini panel, so there's no more commands being sent to the train, so they'll just sit there idling like you see them now till you either pick up this the power cab and run it under manual control, or you restart the mini panel and start them again running that way. This next demonstration will be the same thing as before, except we will run multiple laps. The steam engine on the inside should run 2 laps, and the diesel on the outside should go around 3 laps. And we do this just by manipulating 2 delay statements in the mini panel's program. We just make a longer delay statement so it misses the reed switch the first time around, so to speak, and then it wakes up and sees the reed switch the second time around. So we'll push the button to start the sequence in operation again. So there's our steam engine starting on its first trip around. Now normally, at the previous demo, when it went over the reed switch, it started slowing down, but we've got a delay statement in there that essentially puts the mini panel to sleep, so it's not looking at the reed switch yet. So that train will keep going right on through the siding. Now there it's going through and starting on its second lap. Now that delay statement just timed out, so now the when the magnet on the engine goes over the reed switch, the mini panel will see it this time, and it'll send a set speed 0 command to that steam engine and slow it down to a stop. Now here's our wait between trains, which is still another delay statement. Now the diesel's starting up. Again, there's a delay statement right after the start, right after the command to start the engine, and this delay statement's longer. I think it's about 60 seconds. But again, it puts the mini panel to sleep, so it's not monitoring the reed switch. So when the magnet goes over the reed switch, no commands are executed. Now there's our first lap through the siding. Now here's coming up is our second time that magnet on the passenger car will cross the reed switch, but the mini panel's still asleep, so that train's going to go right through the siding again for its second lap. Now the delay statement just timed out, so now the mini panel's awake, so to speak, and monitoring that reed switch over by the turnout. So when the passenger coach goes over the magnet, it'll send the set speed 0 to the diesel, and it'll come into the siding and stop. So at this point we've done one complete cycle. Now we're starting over again. It'll start the steam engine up for another 2 laps. Now here's the first time over the reed switch for the magnet, but the mini panel is asleep because of that delay statement. So again, that engine's going to go right through the siding and keep right on going. Now the mini panel should have timed out from its delay statement, so this time when that engine goes over that magnet, it sends a set speed 0 command, and that engine will slow down and stop. Now our diesel's starting up, and again it'll make 3 laps around. How you handle these multiple laps, you just time the engines and see about how many seconds they take to go around the loop. Say it, for example, takes 20 seconds to go around the loop, and you want 3 laps, and you'd have a delay statement of maybe 50 seconds or so that it goes 2 laps without looking at the reed switch and then wakes up. It's just kind of a trial and error with a little bit of calculation. Now there's our first lap through. Now this is our second lap coming up. The advantage of running multiple laps was really 2 advantages. One, it's a little more interesting. The system's not so predictable. Now here's our second time through the siding. First advantage is the system's not so predictable. Second advantage is it puts less wear on the turnouts. If you ran this on a display day in and day out, you probably would eventually wear the turnouts out. This is our third time around, so this time it went over the reed switch, it set the set speed 0 command. Now that's the end of the second complete cycle. Here's our delay between trains. Now the steam engine's starting up again. That's the third cycle. I asked one of the designers of S-Helper service, Don Thompson, about throwing these switches continuously. I posed it as what happens if we throw these turnouts every 30 seconds, and here was his reply that came back. He said, I would not try this with the first run of the switches as they had an ABS base, and he said the coil wire could become hot enough to have some plastic melt. He said starting with the second run, bases are metal with an added insulation material. That's quoted right here. And he says most of these parts are brass, but a few have pins or openings that are plastic, and I suppose would be subject to wear. I am not sure if a plastic lubricant could be applied to prevent any possible wear from repeated cycling. So basically these switches should hold up for a while, but that's why we recommend running these things multiple loops between when you throw the turnouts, because that'll greatly cut the wear down on the turnouts. Keep in mind the Loose Ties Model Railroad Club was running one of the LGB turnouts on an automatic passing siding where it's thrown continuously every time the train comes around. Now that was an analog system where they couldn't adjust it for multiple laps, but given that continuous cycling, they did eventually wear out the motor on an LGB turnout and had to replace it. So the bottom line is you probably can wear the turnouts out if you throw them often enough. What we've got here is an automatic route selection demo. We've removed the steam engine, so we just have the diesel passenger train, and we added a station back there. What this demo will do, the train will start up on the outside loop where it is now and go around about twice, and then it'll switch to the inside loop and make 2 laps on that loop, and then the turnouts will throw again, and it'll come around to the outside loop and stop. Now, the routes aren't really too much different. The tracks are almost together, but if you could picture the inside track could be going up a trestle and off yonder and around a mountain and then coming back. So you could have the routes diverging quite a bit. As far as throwing the turnouts, what we've done here, the reed switch, we've still got the single reed switch back there behind the diverging turnout. And what we're doing is when it crosses that reed switch, we delay about 17 seconds, which brings the train around to more or less over here in the middle of the straight section, and we throw the turnouts. So what we're doing is we're timing from when it goes across that reed switch, we're timing it and trying to time it so the train is over here when the turnouts throw, because of course you don't want to throw the turnouts when the train's going over them or you have a wreck. Now to really do this right, if you were setting this up on a more permanent system, you'd probably add a second reed switch over here to a different input of the mini panel, and you'd use that reed switch to give you a positive trigger point when to throw the turnouts. But for the purpose of this video and this demo, we're trying to show what you can do with just the one reed switch back there. And this kind of demonstrates, one of the neat things about the mini panels. If you're doing this in the analog world, you'd have to be continually changing your wiring to make the trains do different things, whereas with the mini panel you just change your programming and you don't have to move your hardware around. So what we'll do now, we'll start the sequence up for this sequence. There's our first lap around. Now a delay statement just timed out. There's actually 2 sets of delay statements. The first one timed out. Now when the engine goes over the reed switch, it starts a second delay statement that delays for about 17 seconds to give that train time to get around the far side of the loop, and then the turnout should throw. There goes our turnouts. Now our turnouts are set to curved, and the train will come in the inside loop. Now there's another delay statement in effect in the mini panel that's allowing that to do multiple loops. That was our first loop on the first lap on the inside loop. Now a delay statement just timed out. Now we'll be looking for that reed switch again back there by the rear turnout. Now we'll time for about 17 seconds, which should allow the train to get over on the far side of the loop. There's our turnout, 17 seconds. Now it's set to the outside loop. Now when it goes across the reed switch back there, we'll get a set speed 0 command and come in and stop at the station again. Now that's a complete cycle of the automatic route selection. Now that train will wait there about 16 seconds or so. There's a delay statement controlling that, and then the whole thing will start up again. There it goes. That shark nose diesel was converted to DCC by Fred Cupp. It's got a Soundtrax decoder, and he put the flashing strobe lights on the front for ditch lights at my request. And the Soundtrax decoder does the automatic toots. There's our second lap around on the outside loop. Now we're in that 17-second delay to get the train over there when the turnouts throw. There they go to curved. Again, notice we're using timing basically to get the turnouts to throw at the proper time. Now we're on the inside loop. Now the first delay statement timed out the controlling the number of laps. Now when that magnet goes over the reed switch back there, it starts that 17-second delay statement. And you can manipulate these delay statements to get any number of loops you want. You could have three laps on the outside loop and 5 laps on the inside loop, because there's delay statements that control each of those. Now we're coming in and stopping. That's the end of our second cycle. And again, we got about a 16-second delay as a station stop here. And this could be longer if you wanted to make it longer. Okay, station stops over. It's starting up. This is the beginning of the third cycle. There's a routine put in the mini panel just to check the momentum of these engines. We're going to take a look now at the steam engine. What the routine does, it just starts the engine up and runs it around the loop, and when it comes in the rear switch over there, it sends it a set speed 0 command, and it'll coast into wherever it's going to stop, and then it holds it there for a few seconds and then repeats the sequence, so we can watch it continuously going around the loop and stopping to see where it's going to stop. And again, that piece of wood marks the approximate place that it's going to stop. There's no turnout commands in this sequence. We have to set the turnout, make sure the turnout's lined up before we run it. The front turnout, you can see, is straight, and we need it to curve, so we can go over here and manually use our push buttons to switch that turnout. Now the rear turnout's lined up for curved already, so we can use push button 4, which is where that sequence happens to be connected to. So I'm going to push button 3. I'm going to select push on push button 3, which will start that sequence. And that engine's being run at speed step 20. Excuse me. That's being run at speed step 16, and it has a momentum value in CV4 of 28. So when that train comes in the siding and goes over the reed switch, it's going to get a set speed 0 command, and it's going to ramp down under its CV4 momentum control. And you can see it comes just a little bit past the block of wood. Now the sequence started it up again. We'll just repeat that same test. Power cab shows, indicates this engine power cab indicates this engine's drawing around 1¼ amps, which seems a little high. It probably means my engine needs some lubrication, perhaps. Here we come back in the siding again. You see now they're drifted about three or 4 inches further that time. Now here's a third lap around the loop. And again, our magnets on the front truck, and when that crosses a reed switch, which is right before the turnout, it sends a set speed 0 command to that locomotive. So there's the third lap. And you see it's coming up just a little in front of the block of the wood, but you can see it stays within about a 4 or 5 inch long area every time that it comes in and stops. This American flyer, Atlantic, was converted to DCC by Chick Viagiano of Chick's Hobby Shop in Gibbstown, New Jersey, back in I think the late 90s. And you can see, in addition to adding DCC and sound, this is an original, one of the first soundtracks decoders. He added a rear backup light, and also underneath the firebox he added a red LED that kind of simulates a flickering firebox. So just to point out this engine, we'll run the momentum test on the diesel now. But again, this block of wood indicates approximately where that diesel will stop when it comes in the siding. And again, the sequence only starts and stops the engine. There's no turnout control in the sequence, so like the front turnout is still curved. We can go over here and use our push buttons, and if you watch, that'll set that turnout to straight, lining it up for the diesel. So the diesel's on push button 4. So I'm going to push on button 4, and that'll start the sequence for the diesel. That's running at speed step 12 with a CV4 momentum setting of about 31. Now the magnet's on the passenger car, so right about now it's sent at the set speed 0 command, and it's going to coast into the siding. Okay, that's our first lap, and it came right about where the piece of wood is located. There's a second lap. Our power cab tells us that this engine's drawing about 0.97 amps, just slightly under an amp. There's our reed switch now at set speed 0 command, drifting into the siding. There's our second stop, again right about where the piece of wood is. We'll do this a third time. We have to make sure it pulls in far enough that the tail of the train isn't hanging out over the turnout. There's a third lap. Going over the reed switch, that the car right about now, the car is on the reed switch. It has a set speed 0 command. And the third time around, stopped about the same place. Now I'm going to push the reset button here, which will stop that sequence. So now both those engines are going to sit there and idle. And I should mention, this is all necessary because we're using one reed switch way back there, and depending on the momentum to bring the trains into the siding and park them at the appropriate spot. If you use 2 reed switches, which you can do, you can put a reed switch, say right about here for this track, and you can put a reed switch right about here for that track and use a much shorter momentum so the trains would stop fairly quickly. You wouldn't even have to go through all this momentum testing routine that we're doing now, but this is just kind of necessary to get them to stop the right place when we're using a single reed switch. We could actually do this for 3 sidings or even 4 sidings if we had more turnouts equipped with decoders. The Video 812, which is a large-scale video, it has 3 sidings, and we used a single reed switch back there in Video 812 to line the trains up on all 3 of the sidings. If you could picture a 3rd siding here, that's how we did it in Video 812, but all using one reed switch. We're not doing the operation in 2 directions in this video, but it would be fairly easy to do. Basically, we'd refer you to video number 811 with the 2 large-scale trains that shows operation in 2 directions. In that video, we use 2 reed switches, and to do it with this system, we would basically take a second reed switch and add it right about here, where the train going this way would go into the turnout, and wire this up the input 12. Right now we're using input 11 for the reed switch. It's on the far end. We could wire this into input 12 or really any of the available inputs. So we'd have 2 reed switches, one for each direction. And you basically just turn one of the trains around and set it up, and you'd make one change in the commands. One train, whichever one was traveling this direction, you'd be waiting for input 12 to go to ground, which would be this reed switch, instead of input 11, which is that one down there. Let's take a closer look at the snap it and the switch here. Again, the green thing here is a North Coast Engineering snap it, and I put a voltmeter here, which I hope the needle shows in the camera, and this is actually charging up to about 22 volts. My command station is set for about 11 volts, I think, so this is charging up to twice the voltage on the track, it appears. But you can see this thing is, this needle's maxed out at 15, but if I throw this switch to curved, you can watch the needle. It is curved. I'll throw it to straight, watch the needle here. You can see how that's charging back up, and it takes a minute to get fully charged back to 22 volts. I'll throw it again to curved. Again, the needle goes down. Now, if I try to throw it now, even though it's almost all the way charged, it didn't throw. So you got to really wait till this thing charges back up to have enough voltage to throw it. As I mentioned earlier, the stock capacitor is 1,000 microfarads, and this one that Fred Cupp added is 4,700 microfarads. If you're not an electronics person, you can sort of make a crude analogy with water glasses. If you think of the stock capacitor, which is here, being this glass, 1,000 microfarads, it holds that much water or that much current, and when you release the water, you get a certain amount of flow of water or current. And here's our bigger capacitor or bigger glass, which holds 4,700 microfarads. The numbers really don't mean anything here. It's just that it's holding more. If I tilt this one, I get more water released or more current. And when we tilt both of them together, that would be, 5,700 microfarads worth of current or water to throw that switch that wants more current. Just for comparison here, I've hooked up an LGB switch to this system. Now instead of the snap it like we were using before for these coil switch machines, the LGB switch can be driven by what they call the switch cat. And notice there's no capacitors on this at all. Apparently it's not necessary. LGB designed these switches to be very low current draw. I think these draw about 1/4 of an amp or so. There's actually a little DC motor in there, almost like what you'd find in an HO engine that drives these switches. So these take about 1/4 amp versus these S-gauge switches all take about 3 amps, it seems. And that's a big difference. You can drive about a dozen of these with as much current as it takes to drive one S-gauge switch. And that's nice for hooking up, like if you're going to drive these things with reed switches, you can drive this directly with the reed switch. If you try to drive this directly with the reed switch, there's so much current it burns out the reed switch, so you have to use relays. So it's much easier to use these type of switches for automatic control. But I've got the push button in my hand here that I can manually control this, and you can see it can be flipped back and forth almost instantaneously. There's no requirement to wait for anything to charge. Again, that's because it's drawing a very low amount of current. So from my own personal point of view, I wish the S-gauge switches would have been designed more like these things that work off a lot lower current. But since I'm probably the only person in the world, or one of the few people in the world who cares, that's probably not going to happen anytime soon. Here's our control unit hooked up for some simple testing. For this part, notice there's no track and no trains. The accessory decoders are here because this unit's from a previous video, but you don't even need the accessory decoders hooked up. What we're going to do is run a little test sequence that consists of about 9 commands, and we'll look at those commands later, but it simply sends a command every 2 seconds to change the turnouts. Now when the mini panel sends a command, this little red LED here blinks. If I push the reset button, that causes it to blink also. You should be able to see it blink right now when I'm pushing this button. So I'm going to start the test sequence by pushing the button number 2 here. And now what's happening is that mini panel is sending a command every 2 seconds, and you can see every 2 seconds this blink, so you can sort of see you're communicating with the mini panel. And I should mention I've got the reed switch number 11, the inputs for that jumpered with this blue wire, so it looks like to the mini panel there's a magnet being held over reed switch 11 holding it continuously closed. What the test sequence looks for, it looks for if the magnet, if the reed switch 11 is closed, then it sends these commands every 2 seconds. So we're executing the test sequence, and we can visualize we're sort of communicating with the mini panel by seeing that light blink. Now if I push the reset button here, that'll stop it from sending commands. So now the mini panel is back to the idle state. We've got a single turnout hooked up to the system now. This turnout is hooked up to accessory decoder 9, so the mini panel sees this turnout as turnout number 9, and this will be turnout number 8, but it's not hooked up to anything yet. There's no turnout 8 in the system. So what happens when we start that same test sequence, the mini panel will send commands to throw both turnouts 8 and 9 straight. It'll send them 2 seconds apart. And then it'll send the commands to set them to curve 2 seconds apart, and they're staggered. Let's start the system up here. There it went to straight. Now 4 seconds later back to curved. 4 seconds later back to straight. we need to keep about 4 seconds between commands to give these capacitors time to charge up. They need about 4 seconds to charge up. This is blinking about every 2 seconds because it's sending a command to the other turnout 2 seconds after it sends a command to this turnout. So there it changed. Now that was turnout 8. There's turnout 9. That command was turnout 8. That command's turnout 9. So we're actually, if both turnouts were hooked up, we'd be sending commands 2 seconds apart. But with just one turnout, you see it changing 4 seconds each. 4 seconds each between changes. We'll push the reset button to stop it here. We've got the same thing before, single turnout hooked up to accessory decoder 9, but we've added the voltmeter over here. And this voltmeter, as you see it, the needle's pegged at 15 volts. This capacitor apparently charges up to about 22 volts or something like that. But if you watch the needle on that capacitor, I can manually throw the turnout using these buttons. I'll switch it to straight, and you can see how that needle went down to 0 and then it charged back up. Now I'll throw it back to curved, and again you can see the needle went over to 0 and it's charging up to about 15 volts. So it looks like it takes about 3 or 4 seconds to get charged back up. And if you try to throw these switches too soon before the capacitor charges, they won't throw. You don't have enough current. So let's start that same test sequence, and we can watch the voltmeter go up and down as it throws. There it threw, and you can see the voltmeter is charging up again. Now to curved, and it's charging up again. Now to straight. You can see how each time that turnout throws, the voltmeter goes down to 0, and you can watch the needle swing to the right as the capacitors charge up again. And again, you can see like it takes about 3 or 4 seconds for that thing to get charged. Remember, it's going up to 15 volts there, and it actually needs maybe another second to get all the way to 22 or 24 volts, whatever it's actually charging up to. Here we are with both turnouts hooked up now. Now the voltmeter again is hooked across just this capacitor here. The voltmeter's not showing anything about these capacitors over here. But what the mini panel will do now is it's the same sequence, but it'll be changing each turnout every 2 seconds. So it'll give each turnout 4 seconds to charge the capacitor up. Let's start that in operation. You can see it's changing this one to straight. 2 seconds later, that one to straight. 2 seconds later, that one to curved. 2 seconds later, that one to curved. And so again, just repeating, it's changing turnouts 2 seconds apart, but it's giving each turnout, and thus each set of capacitors, 4 seconds to charge back up again. And we can stop that sequence with the reset button here. Now push the reset button. They're both in the curved position, so we can start the test sequence up again if we wanted to. This isn't a big deal. You don't need to be concerned about this if you're operating the system. But these test sequences we've gone over are just some ways you can verify when you're constructing one of these that your mini panel is actually talking to the turnouts, and you're actually able to communicate with it. Here's the control panel that you see used in this video, and this was actually built for earlier video number 806 and reused for this video. Number 806 video was a point-to-point operation with 2 turnouts, and what you see on the picture here's an accessory decoder for the 1 turnout with the extra capacitors. Here's an accessory decoder for the other turnout with the extra capacitance added. There's actually 2 capacitors here. Over here is our mini panel, And here is our power control panel, which is part of the power cab. Here's the wiring diagram for that unit we just looked at. Again, you can see the track layout is for a point-to-point, but if you just visualize where these bumpers are on the end, if this being extended from this bumper onto a loop, this loop continuing around and coming in where the other bumper is, you basically have the same loop as we see in this video. And again, this was for video number 806, but this was built to be an interface. You can see it's marked interface here. This unit was built to interface with somebody else's layout, which is why the accessory decoders were on the control unit. Now the advantage of doing this is you've got your push buttons up here on your control unit, where it's easy to manually control the turnouts with the push buttons. The disadvantage is that the wiring is a little more complicated, but this is basically the wiring of what we're seeing in this video. This wiring diagram is from video number 811, which is the large-scale automatic passing siding. It basically does the same thing as the previous wiring diagram, except it's a little simpler to use, simpler to look at, because it wasn't made to interface with another layout. In this case, the accessory decoders are out on the layout, and they can wire directly to the track, since the accessory decoders run off the track current. Here you can see there's one hooked up over here, and on the right there's one hooked up over here. This same setup would work for the S gauge. The only difference is instead of these switch-cat decoders, which were used for the large scale, you would use the snap-it accessory decoders with the extra capacitors for the S gauge. And where these turnouts are marked LGB, which are the large scale turnouts, this would be S helper service turnouts or American Flyer turnouts or whatever brand of S gauge turnouts you were using. The main challenge with the S gauge turnouts is just getting enough amperage to throw them, since they take a lot more amperage than a large scale turnout. Now this drawing shows two individual reed switches for running the trains opposite directions. In this video for the S gauge, if you recall, we had a single reed switch back here upstream of the diverging turnout, but as I mentioned in the video, you can have as an alternate to having a single turnout here, a single reed switch here, you can have individual reed switches in the siding, and that's what this is showing here. In this video, one reed switch was hooked to input 5 and the other reed switch was hooked to input 6. Here's another wiring diagram. This one's from video number 812, which was the same as 811, except it showed a 3-track. If you look down at the bottom, you see there's 3 tracks for the passing siding. Very similar, except we have two. Now we have two decoders. We have two accessory decoders back here where the trains come into the yard to control each one of the turnouts. For large scale, you can take on the exit end of the yard, you can take the switch motors off, and the switches will just kind of float. The engines are heavy enough to push through them without having a motor. Now for S gauge, you would probably need to have turnout motors here and another 2 accessory decoders down here. But the point is, with this DCC, it's fairly simple to extend a 2-track yard like you've seen in the video to a 3-track yard or a 4-track yard or even more. It's just a matter of adding turnouts, accessory decoders, and the appropriate commands in the mini panel. From this point to the end, we'll be going over the commands used in this video. The NCE mini panel instructions include this menu navigation chart, which tells you what entries you have to type in to program the mini panel. For example, if we were going to select logo 3, once we're in the setup mode, you've got setup, review, and test, but for programming, you're in the setup. To select logo 3, you would enter a 3 to tell it you're going to select logos, and then a 1 for the select statement, and then the logo number. So you'd have a 3, 1, 3 to select logo 3. Then to tell that same loco to go speed forward 10, you would have a 3, 2 for speed, and then a 2 for a 28 speed step mode, and then the speed value 10, and then you'd select enter to select the direction as forward. So it'd be a 3, 2, 2, 10 with the forward direction. And then to say, for example, to wait until input number 5 is grounded, you'd put in a 5 for other, and then a 2 for a wait, a 1 for a ground, and a 5. So you'd have 5, 2, 1, 5 to wait till input 5 was grounded. Note you also have the open statement, which you can use with electric eyes, but the ground statement is used with the reed switches. Whenever I programmed the mini panel, I would sit down and work my way through this chart to enter each command, and that did the job, but it took a while. Then I observed people who were smarter than me, like Fred Cupp. They weren't doing that. They'd create an entry column, which basically gave them a summary of the numbers they needed to type in. Here's the entry column, the second column. We've got these numbers. For example, the ones we just did, select loco 3, there's our 313 in this column, and we don't need to refer to the chart, the navigation chart. We just use these numbers to punch them in. It's much faster and much easier. Again, the speed forward 10 we just looked at a minute ago, 3, 2, 2, 10, and the forward is documented here. Then the wait till input 5 is grounded. That's the reed switch being closed, be a 5, 2, 1, 5. And I went through the commands we used in this video, and basically I believe we only use 8 unique commands to do everything done in this video. And the only thing that varies is a number in red. That changes. For example, for putting accessory 7 to reverse, which means throw turnout number 7 to curved, we'd use a 7, that the 1 tells it to do the accessory, the 7 tells it which accessory, and the 2 tells it's curved. If it was accessory 10, it would be a 10 instead of 7. So we're basically using all these commands over and over, and the only thing that's varying is the item in red here, and the rest of it stays the same. So we'll basically use these 8 commands, link the input 9, that's a 539, or whatever number you're using here changes in red, and we're using just reed switch number 5 in this video, so it stays the same for this video. The accessory 10, we're using accessories, which is a switch decoders, turnout decoders, that is. We're using either 7 or 10, and they're going to be either curved or straight. So in this case, it's 172 to throw turnout 7 to curved, or it'd be 171 to throw turnout 7 to straight. And if it was turnout 10, we would just use a 10 here instead of a 7. And again, our delay statement 5124, 4 gives you 4 quarter-second delays, which means delay 1 second. Selecting loco, again, if you're selecting a different loco number, you just put a different number in here. We're using 3 for the Mac, which is long address 3, and 211 for the Steins steam engine, and 470 for the black LGB diesel. Then our speed forward step, it's always the same, 322, and then whatever speed numbers, the 10 here is used for speed step 10, but you just put a different number between 1 and 28 for whatever speed you're selecting. Here's almost the same delay statement, except we're selecting the 4-second version. You can have quarter-second delays or 4-second delays. If we select the 4-second delay and we want 2 of them, which is 8 seconds, we'd have 5112, and this number here would change if you were delaying for a different amount of time. Then the no-op command, which is basically a do-nothing command, just go to the next step. That's a 551. This page documents our configuration of the mini panel, and also the use of the first 5 push buttons. Of go into our configuration memory, there's 6 variables here, and they're all default except for 2. The default for memory address 0, which is a cap address, is 3. And if you use this with a power cab, like we're doing in this video, it has to be unit number 3. However, if you're not using a power cab, it could be a different cab number. And then going to memory address 3, continuous memory, we put a 10 in there. The default's 0, but we're changing that to 10. And that means the memory for input locations 10 and above will be continuous. In other words, you don't have to use a link statement like you have to do for non-continuous memory. Then memory address 4, which the default there is also 0, we've set that to 10. And that means that the mini panel won't pull inputs 10 and above, or said another way, it won't be continuously looking at inputs 10 and above. In previous discussions, I've referred to the mini panel sometimes as being in an idle mode. That's actually not quite correct, because even when it's not executing any commands, it's still polling, in this case, the first 9 inputs in case someone pushes any one of those buttons 1 through 9, it'll execute those commands, but it won't pull inputs 10 and above in this case. Now let's look at the buttons. We've got 5 buttons that are hooked up and used for this video. The first button links to input 17, and that's normal operation. And then the other buttons, the next 3 are test sequences. Button 2 links to input 10, which tests the read switches. Button 3 links to input 13, which is a momentum test for the steam engine. Button 4 links to input 15, which is a momentum test for the diesel. And then button 5 links to input 22, which is the automatic route selection sequence. So next thing we'll do is look at what happens when we push button 2, which starts our test sequence for the read switches. This sequence of commands is used in demos 1, 8, 9, 10, and 11 for testing the read switch. And basically what it does, it throws a turnout every 2 seconds if the turnouts are hooked up. It basically consists of these commands. We start out on input 10, step 1, with a command that says wait till input 11 is ground. That means it's looking for the read switch to have a magnet go over it, which will close it, which creates the ground condition. And the actual sequence of numbers is a 5, 2, 1, 11, where 11, the 11 specifies the number of the input. It's input number 11. Basically, that translates to wait for read switch number 11 to be closed, which is when you close it, the resistance goes to essentially 0 and it's grounded. That happens when you're holding the magnet over the read switch, or in the case of demos 8, 9, 10, and 11, when we have that wired across the 2 read switch terminals for testing. Then the next step says accessory 8, norm 181. That says throw turnout number 8 straight, and the 8 specifies the turnout, and the 1 specifies that it's straight. Then we have a delay statement, delay a quarter second times 8, 5, 1, 2, 8, and 8 specifies how many delays, so that works out to a 2-second delay. A quarter second times 8 comes out to 2 seconds. Then we have accessory 9, norm 191, and that says throw turnout number 9 to straight. And then from here it basically repeats. We delay 2 seconds, we throw turnout number 8 curved, delay 2 seconds and throw turnout number 9 to curved, delay 2 seconds, then we go back to input number 10 and repeat the test. In other words, this command linked to input 10, 5, 3, 10, and the 10 tells it where to go. It goes back up to input number 10 and starts these steps over again. And what this does, if the turnouts are connected, it'll throw one of the turnouts every 2 seconds. There can be one turnout connected, as was the case with, I believe, demos 9 and 10, or 2 turnouts, both turnouts connected, as was the case with demo number 11. In demo number 8, we had no turnouts hooked up to it. All it did was flash the light on the mini panel so we could see that it was sending commands. So this works for no turnouts, 1 turnout, or 2 turnouts for testing purposes. Here's the commands for testing the momentum of the steam engine. And this is set up so we manually align the turnouts for the train being tested. There's no turnout commands in this sequence since we're just running the same engine around and around over and over. And this sequence is used in demo 5 in this video. And here's the command. First thing we do, we select loco 302. That's a 3-1, and the 302 in the red is the variable. That's engine 302. And over here it says select loco number 302, American Flyer Atlantic steam engine. The next command is speed forward 16. And again, your variable here is the red number and 16. Whatever you put in here from 1 to 32, actually from 0 to 32 determines the speed. So we're starting the loco at speed step 16. Here we're delaying 8 seconds just while this is just a delay statement. It's not really used here, but it's used in other parts. It's just 8 seconds while the train exits the siding area. Now the train, at this point, the train is traveling around the loop, and our mini panel is waiting at this statement. It's waiting for input 11 to go to ground. That's 52111. 11 specifies which input. That basically says wait. That says wait for the train to reach read switch number 11. When the magnet on the bottom of the lead truck on the locomotive goes over that read switch, it'll close the read switch, which will decrease the resistance to essentially 0, which will create the ground statement that satisfies this statement. So when that engine reaches the read switch, this condition will be satisfied, and the mini panel will go on to the next step. The next step says speed forward 0, 3220. So there's our speed command again, but with a 0. That says stop the loco, speed 0, a set speed 0 command. Now we have a delay statement, and while this is happening, it says delay 4 seconds times 5, 5115, and the number in red is the variable. It says delay 20 seconds before starting up again. This has to be long enough to for the engine to ramp down its controlled momentum, to ramp down to 0 speed and sit there for a second, then start up again. In other words, if you make this too short, the locomotive will never come to a complete stop. It'll still be ramping down under momentum control and then start up again. So this time delay has to be at least long enough for the engine to come up to a complete stop so you can see where it stops. Then our last statement says link the input 13, 5313, and the 13 is the variable. It says go back to input number 13 and repeat the test sequence. So that at this point it goes back up to the top and starts over. So this sequence will keep running that Atlantic steam engine around and around and around, and you can watch several times to see where it stops when it's done coasting under momentum. And whenever you're done executing this test, then you hit the reset button to stop this sequence. When we push button number 4 to test the momentum on the shark nose diesel, this is a sequence of commands we're executing here. This is used in demo 6, which tests the diesel's momentum. And basically you push, we haven't hooked up the button number 4, so when button number 4 is pushed, it starts executing commands at input 15. And basically it says select loco number 1216, which is the America model shark nose diesel. Actually, that's an America model chassis with a custom shell on it. Then it starts the loco up at speed 12, delays for 8 seconds. It just does nothing while the train exits the yard area. Then again, it waits for the train to reach read switch number 11 and for the magnet to ground the read switch, or I should say close the read switch, which creates the ground condition that the mini panel is waiting for. Then it sends a speed step set speed 0 command, speed forward 0. In other words, that's speed 0, which says stop the loco. So at that point, the loco starts slowing down under its momentum. Now we've got a delay of 16 seconds before starting up again. And again, that loco has to get stopped within 16 seconds so we can observe where it's stopping at. Now it says link to input 15. Go back to input number 15 and repeat the test sequence. And I think we mentioned it earlier, but again I should say, if you put the reed switches inside the sidings rather than upstream of the diverging turnout, then you don't need to go through all this momentum testing. But since we're putting the reed switch upstream of the diverging turnout for this video, we need a fairly exact amount of momentum. If we use too much momentum, the train will drift right through the yard and end up sitting on the exit turnout, which is no good. If we use too little momentum, it won't drift into the yard far enough, and it'll end up with the caboose or the tail end of the train sitting on the incoming turnout, which again is not a good condition. So we have to get approximately the right amount of momentum by doing these tests to get the train to pull into the yard and be clear of both turnouts. Here's the sequence, what we call normal operation for two trains, and this is used in demos 2 and demo 3. Demo 2 is where each train went around the loop once. Demo 3 was the same thing, except the steam engine went around twice and the diesel went around 3 times. So when we push button number 1, that says link to input 17, which brings us to this step here. And basically that says set the front turnout number 9 curved, set the rear turnout number 8 curved. That sets both the turnouts curved, which is the track the steam engine's running on. Then we select loco number 302, which is the American Flyer Atlantic steam engine. Then we send a speed forward 16 command, which starts the inside locomotive up. Now we have a delay of 48 seconds as this appears here after the train starts. That's enough for the steam engine to go around 2 laps. So this command here, as shown, is for the steam engine to run 2 laps. We say delay 4 seconds times 12, which gives us the 48 seconds. If we wanted to run just 1 lap, we'd say 8. We'd put in 8-second delay. And this delay is what we do is we measure the time for the engine to go around 2 laps, and when it gets in the middle of the second lap, try to time it at that point, and that's the delay we try to put in. There's nothing precise about this. If you make it too long, it'll go an extra lap longer than what you thought it was going to go. If you make it too small, it'll go a lap less than what you thought it was going to go. So nothing critical about this. Now the next command is essentially a dummy command. We say accessory 2000 norm. I think the accessories can go up to 2044. Well, we've got accessory 8 and 9 as our 2 accessories, so 2 turnouts. So we have no accessory 2000 in this layout. But what we're telling the mini panel to do is send a command to accessory number 2000 to set it to straight, assuming it was a turnout. And what this is a dummy command just to blink the LED. So by watching the mini panel, what we can do is when this delay statement times out, it'll send this command to the non-existent turnout, which will cause the LED on the mini panel to blink, and that way we can see where it timed out. It's just an observational thing. Now as we continue on, we have wait for reed switch number 11 to be closed. That's wait for the engine to go across the reed switch, which means it's entering the siding. We send a speed forward 0 command. That's a set speed 0 command, which tells the inside track loco of the steam engine to stop. Now going to the next statement says delay 20 seconds. That's the delay between trains. Again, you can vary this as much as you like. And basically this 20 seconds gives the steam engine time to coast to a stop, and it doesn't really have to be to a complete stop before you change the turnout, but it does have to be long enough that the cabooses moved over the turnout. If you made this too short, you might end up throwing the turnouts while the steam engine's caboose was still going over the turnout. So we delay 20 seconds, then we set the front turnout straight and the rear turnout to straight. Next command's a do nothing command. Now we select loco number 1216, which is the D&H shark nose diesel. We send out a speed forward 12 command, which starts the outside track loco, which is the diesel. Now we delay 72 seconds, 4-second delay, 18 4-second delays, which gives us 72 seconds. And this is enough to get the shark nose to go around 3 laps. And again, we send that dummy command to set 2000 norm. And so when the mini panel sends that dummy command to a non-existent turnout, it flashes the LED. And again, we can see where the diesel actually is when this delay statement times out. Now we're going to, again, wait for reed switch number 11 to be closed when the magnet on the bottom of the first passenger car goes over the reed switch. The mini panel will send a set speed 0 command, speed forward 0, which will tell the diesel to stop. So the diesel will start ramping down under momentum control. We're going to delay 16 seconds between trains, 4-second delays. Then we'll go back to input number 17 and repeat the sequence. And again, this delay here can be longer if necessary. It can't be too short, though, or you'd be throwing the turnouts too soon. Here's the commands that are used in Demo 4, which is the automatic route selection, and that's controlled by push button number 5 that activates input number 5, which links to input number 22, which starts this sequence. And the general mode of operation is it starts on the outside track by the station, does 2 laps on the outside track, changes to the inside track and does 2 laps, changes back to the outside track and stops at the station. So the first set of commands we send are these 2 commands to set the turnouts to straight, to line it up for the outside track. Then we select loco number 1216, which is the diesel. Then we start it forward with our normal operating speed, which is speed step 12 for this diesel. Now here we delay 16 seconds after the train starts up, and that delay causes the mini panel to wait there and not do anything for 16 seconds, which allows the train to get around 2 laps. This time isn't critical. If it's too short, you'll get less laps than you expected. If it's too long, you'll get more laps than you expected, but it's not critical. Now this next statement here shown in green is a dummy statement. It just tells the mini panel to throw accessory 2000 to normal. If that was a turnout, it's saying throw turnout 2000 straight. There is no turnout straight, but a turnout 2000 to throw. But what it does when that mini panel sends that command, it causes the light to blink, the red LED to blink, so you can see where that delay timed out in relation to where the train is. Now the next thing is wait for reed switch number 11 to be closed. So that's when the passenger car with the magnet goes over the reed switch just upstream of the entrance to the yard. Now this next statement is critical here. It says delay 1/4 second times 68. In other words, that's 68 1/4 seconds, which works out to 17 seconds. And we use the 1/4 second command because that way we can adjust it by 1/4 second up or down as we need. And we call this statement critical because this allows the train to get over to the other side of the loop. As you watch the video, it's the left side where the train is over on the left side of the layout, away from the turnouts. And you need to get it positioned about there before you throw the turnouts. You don't want to throw the turnouts while the train is going over them. You could call this a virtual reed switch. If you're really doing this on a real layout, you might just want to mount a reed switch over in that location. But here, for the purposes of this video, we were trying to use just one reed switch to demonstrate what you can do. So when the train, when this 17 seconds times out and the train is over on the left side of loop away from the turnouts. Then it changes the two turnouts to curve. That's these two commands here. Then it delays 24 seconds, which will allow it to do about 2 laps on the inside loop. But again, this delay is not critical. Here we have our dummy command, again, turnout number 2000 straight. This just blinks the LED. We can tell where the train is for observational purposes. Now we have another wait for reed switch number 11 to be closed. This waits till the passenger car with the magnet goes over the reed switch upstream of the diverging turnout back at the rear of the layout. Now here's our second critical command we're calling a critical command. Again, it says sleep for 17 seconds after the reed switch to get to the middle of the main line. Again, we're doing the same thing. We're having a quantity of 68 quarter-second delays to try to position the train over on the left side of the layout away from the turnouts. So at that point, we set the turnouts back to straight, which will line the train up by the outside track. Now here's our wait for reed switch number 11 to be closed. And when the train comes around again over that reed switch, we send it a set speed step 0, set speed to 0 command, speed forward 0. That's right here. And that causes the engine to ramp down and stop the diesel at the station. Here we have another delay statement, delay 16 seconds. This is the length of our station stop. This could be made a lot longer or possibly shorter. It's nothing critical about that. It's just how long the diesel sits at the station before it starts up again. So when that command times out, then we say go back to input number 22 and repeat the sequence. So that takes us back up to the top here, and we reset the turnouts. This really isn't necessary because they already should be lined up, but this is just to make sure everything's lined up properly. But then the sequence starts repeating, and this sequence will keep repeating until you stop the mini panel.